All right, so now I'm going to talk about how modified equation analysis relates to geometric integration. Okay, so let me state the following theorem, and then I'll prove it for the special case of symplectic integrators applied to Hamiltonian systems. So the basic theorem is that whenever the flow map of a given differential equation possesses some geometric properties, such as the existence of first integrals, time reversibility, volume preservation, symplecticity, and numerical discretizations. And the numerical discretization exactly preserves these properties. Then what will happen is that the flow map of the modified differential equation will also satisfy these geometric properties. All right, so let's prove this in the context of symplecticity. Okay. So we'll consider the case of symplectic integrators. In detail. Okay. So if you recall, it's like the modified vector field can be recursively defined. By the following. Okay. So you have this delta fi plus 1 term, which is the limit as tau goes to 0 of the difference between the one-step method and the exact flow of the modified vector field up to the I recursion index divided by tau to the I plus 2. Okay, and then we introduce some notation. Okay, which allows me to sort of just simplify this expression. So I'm going to just think of this exact flow map tau. Every time I see that, you should really think of the flow of this modified vector field. Okay. All right. So if you have that, then what happens is the following. So then we obtain the following okay, that you can write down essentially the linearization of this the linearization of the numerical method, right, is equal to the linearization of this, it's like exact flow of the modified vector field plus error term which looks like tau to the I plus 2, the partial of this modified vector field term, right, this correction term, plus something which is big O of tau to the I plus 3. Okay, and then we consider the following. Let's call it f tau, which is defined to be 1 over tau to the I plus 2 times the following. So this is the term you look at, if you will. It's like when you're trying to check symplecticity, right? At least part of the term you look at. Okay, so you're basically conjugating the symplectic matrix. It's like by the linearization of the map. Okay, but what you sort of assumed was that both the, it's like, so by the inductive hypothesis, it's like this is the exact flow of a Hamiltonian vector field. So this is symplectic, and then this is, it's like a symplectic integrator. I'm sorry, this is the one-step method, right? So the one-step method is symplectic. So this, this thing is just going to be J, and then the same thing is true here, that this is the flow of the of a modified Hamiltonian vector field, right? That's sort of the inductive assumption, and then you want to show that this correction, the next correction term, is also a Hamiltonian vector field. All right, so both of these things correspond to symplectic maps. Okay, so since both the numerical method psi h and phi h, which is the exact flow of this modified vector field, are symplectic. I guess it's with respect to tau, are symplectic. Right, so this implies that we have that basically f tau is 0. Okay, so but I can use this expression here to expand that using this. Okay, we have that f tau looks like minus partial of this sort of correction term, tau j, then this linearization of the exact flow of the modified vector field, right, minus the transpose or the linearization of the exact vector field, the modified vector field, times j times this linearization of just this sort of new correction term, if you will, plus big O of tau. Okay. Okay, all right. And then you use the fact that the linearization of this flow map is near the this, of course, the flow map, it's like is a near the identity transformation, and it looks like basically the identity plus tau times something, right? So if you just if you're sort of dropping all terms which are linear and higher order in tau, then this is just the identity basically. So that simplifies. So this becomes minus d2 delta fi plus 1 transpose j, right, minus j d2 delta fi plus 1 plus something which is big O of tau. Okay, and then if you take tau going to 0, then you just get this thing is equal to 0. Okay, you get 0 is equal to minus this condition here. All right, so this is what is called a condition for infinitesimal symplecticity. Okay, so this implies that delta fi plus 1 is infinitesimally symplectic. And this implies that it is locally Hamiltonian. Which is to say that locally you can write this as the Hamiltonian vector field of some Hamiltonian. Okay, so right, so again this sort of tells you that well, you start with the inductive hypothesis is that because f tilde is 0, of course it's just the original vector field, which is by assumption Hamiltonian. And then it's like what this induction says is that if the sort of, the f tilde I is Hamiltonian, then the additional correction you introduce is also going to be, or can be thought of as coming from a Hamiltonian as well. So, so if every term it's going to be Hamiltonian, then you would expect again that, this entire sequence, it's like of approximation, sort of, better and better approximations, it's like of the one-step method, it's like all correspond to symplectic maps. Okay, so I'll just stop there.